And in this presentation, I show you that heartbeat dynamics is an output of a non-chaotic dynamical system driven by physiological noise. Okay, let me start with a brief introduction about physiological system modeling. Okay, a physiological system can be modeled as a stochastic system or as a deterministic system. According to this choice, different techniques can be used to analyze the data. If you assume that the system is stochastic, we may consider the information theory framework and the probability laws. Instead, if we assume that the system is deterministic, we may be interested on the regularity of the system. So we can use the Lyapunov exponent, for example. But the problem is that the techniques based on the assumption that the dynamics is deterministic may be invalidated by the presence of the noise. Now, physiological system, it is well known that show nonlinear deterministic dynamics, so they cannot be considered as fully stochastic. But there are also evidence of the presence of a stochastic component that intrinsically modifies the dynamics, so they cannot be considered as fully deterministic. So the best way to model this kind of system is to consider them as deterministic systems driven by dynamical noise. Oh, luckily here there's a problem, but in my original version it was more clear. In any case, this is an equation describing this system, and you can see that each step depends on the previous steps by means of a deterministic map F that is unknown in general, and a random variable that is assumed to be Gaussian in general. And now the question is how to determine whether the map F exhibits regular or chaotic behavior. Okay, to answer this question, the problem is that there's no methodology able to identify regular or chaotic behavior in deterministic system driven by dynamical noise. So, in our work, our first aim is to develop a novel methodology that can do this job. And our second aim is to apply this methodology to real heart rate variability time series to determine whether the cardiovascular system is regular or chaotic. Okay, so in the next slides, I show my methodology. Let X be a time series of length capital N. The first step is the construction of an auxiliary PQ phase space starting from the samples of the time series. Why this? Okay, the reason is that there's a formal proof that you can find in this paper of the fact that for a time series generated from a regular map, the trajectory in the PQ phase space remains bounded. And you can see an example here in blue. Instead, for a time series generated from a chaotic map, the trajectories in the PQ phase space tend to cover the whole space with growth rate equal to square root of n. As you can see an example in orange. So once we have this PQ phase space, we compute the mean square distance between points. And observe that this quantity, m of n, is the mean square distance in the PQ phase space between pairs of points that are separated by a lag of length small n. For this reason, n should be much smaller than capital N. Otherwise, the mean does not have sense. In this graphic in orange, you can see the profile of M. Observe that there are several oscillations. Well, we don't care about these oscillations since we are only interested on how this quantity is growing. So we compute the modified mean square displacement, and you can see the profile in green. Well, okay, you can note that until this point, we did not take into account the presence of the noise. So in the next step, we deal with this aspect. Okay, to do this, we add an oscillatory component to the modified mean square displacement, whose amplitude is modulated by a function of the signal to noise ratio, G. Okay, the key idea behind, let's say, the intuition behind this function G is that it should take values close to zero when the noise does not have a strong impact on the dynamics. Instead, it should take its maximum values when the noise has a strong impact on the dynamics. And note that here, I'm sorry for this frame of, in any case, observe that sigma is the noise standard deviation, and when we analyze heart rate time series, so real time series, this quantity is estimated by using the methodology described in this paper by Andrea Scarciglia and co-authors. Okay, a function that does the job I said is, for example, the inverse Gaussian probability density function. Okay, why this choice? There are two main reasons. The first one is that it produces good performance on synthetic data, really good performance. And the second is a physiological reason, since the inverse Gaussian is the distribution of the intervals of an integrated Fire model driven by white Gaussian noise and a positive drift. Okay. Well, once we have the quantity d tilde, okay. Once we have the quantity d tilde, we want to establish. Okay. We want to establish whether its growth rate is linear or not. So to do this, we compute the linear correlation coefficient between the vectors u, given by 1, 2, and tilde n cut, and the vector d tilde of 1, d tilde of 2, until d tilde of n cut. This correlation coefficient, that we call Kf, okay, it's here. You can see an exemplary profile of for different values of f in the interval 0, pi, for a regular map in blue, and in the chaotic case in orange. Observe that when I say regular or chaotic map, I mean a time series generated from a regular or from a chaotic map. So I use this terminology even later. Okay, and to obtain only one value, we perform the previous steps for different values of f in the interval 0, pi, and then we compute the median. The median k takes values in the interval 0, 1, and it is a measure of the regularity of the time series. When it is above the 90th percentile, the dynamics is classified as chaotic. Instead, when it is below, the dynamics is considered regular. Okay, so this is the methodology. The first thing we do is to test it on synthetic data. In particular, we consider the logistic map, both irregular and the chaotic regime. In the left side, you can see different PQ phase space, in blue for a regular map, and in orange for a chaotic map. In the first line, we analyze noise-free time series. Instead, in the other lines, we consider noisy time series with different level of noise. Okay, instead, in this graphic, you see in the y-axis different values of k, and in the horizontal axis different percentage of noise standard deviation. These box plots are obtained on 100 different time series. In blue, you see the results for regular time series, and in orange for chaotic time series. Observe that when we add the noise at the highest level that we consider in this analysis, that is 10%, while the PQ free space of a regular and a chaotic map are quite similar, at least macroscopically. The k-values computed in the regular case and in the chaotic case are significantly different. And so, we can say that this method works well on synthetic data. And now, we are ready to move to the results on real data. Okay, our dataset is composed of 38 heart rate variability time series of healthy subjects. One half are young adults and the other are elderly adults. During the recording, the subjects were in resting state and they were watching the movie Fantasia. In the blue, you can see an exemplary heart rate variability time series of a young, and in green of an elderly subject. First, I show you the PQ free space, an exemplary PQ free space for a young time series in blue, and for a time series of an elderly subject in green. I think that the similarity with the PQ free space of a regular map is quite clear. And this impression is confirmed even by considering the profile of KF for F in 0 pi. In blue, the results on the young time series, and in green, the results for the elderly time series. For each value of F, K of F is below the soil 0.9. And to be precise, the mean K value computed in the young group is equal to 0.029, and the mean K value computed in the elderly group is equal to 0.002. In the first column of this table, you see the mean noise standard deviation estimated by the methodology of Hertzschild quarters. And observe that this noise standard deviation are different between the young group and the elderly group. So, after this analysis, since K is smaller than 0.9, we can say that the heart rate variability is the output of a regular dynamical system driven by dynamical noise. Okay, so we answered the initial question. And maybe you're asking, why? Why is it so important to know whether the cardiovascular system is regular or chaotic? Well, there are several reasons. The first one is that we want to get a better knowledge of the system. So we discover it's regular, and we also discover that aging does not modulate the dynamics in terms of regular versus chaotic, but it modulates physiological noise, since we find different noise level in the young group and in the elderly group. And once we have a better knowledge of the system, more specific model-based biomarkers can be used, and it's really important in medicine. And the last one is an historical reason, since we want to answer a question remain unresolved. Indeed, in 2009, an important journal, Chaos, posed the provocative question, is the normal heart rate chaotic, to encourage researchers to get engaged with this problem. But in the end, the question remained unanswered, since the conclusions were invalidated by the presence of the noise in the data. So to conclude, we developed a novel methodology able to identify chaotic dynamics in noisy deterministic systems from experimental time series. The framework provides a normalized index of the regularity of the series. Moreover, this method is general purpose, since it can be applied to each kind of time series. We validated this method on synthetic data, and we can conclude that the cardiovascular system shows regular dynamics driven by physiological noise. So we can add the last cross in our scheme. Thank you for your attention. And sorry for this problem. I mean, it was nicer.
Are there any questions?
Okay, so
So you're talking about, you've got these elderly people over 68 and then these young people up to 34, and the chaotic one was in the younger people for the noise, and the elderly had the logistic, is that correct?
Sorry? Okay.
I feel like I missed something.
Ah, you mean here?
Yes.
Ah, yes. This is the noise standard deviation. This is the mean noise standard deviation estimated in the young group. So, for each time series, the noise standard deviation is estimated by the methodology in this paper.
This is the synthetic data, though, yes.
No, these are the real data.
This is the real data. Okay.
Yeah, real heart rate variability time series. The subjects were
Go to the last slide.
Here?
Keep going.
No, then
There was a circle and then
No, just before that.
just before. Sorry.
yeah.
So, can you describe these two images versus what you were just saying?
Yeah, these are the PQ phase space. If you remember, the first step of the method consists in the reconstruction of this auxiliary phase space, starting from the samples of the time series. Well, before I show you these phase space that are obtained analyzing synthetic time series.
Right.
Okay. And instead, in this case, I do the same thing, but analyzing real heart rate variability time series. But the passage, the computation is the same.
Right.
And I was saying that these trajectories, I mean, so they are real time series, are quite similar
To those.
exactly
And so
to those trajectories that are obtained analyzing regular time series, regular synthetic time series.
okay, and so the elderly ones are the first one, and then the younger ones are the second one for type.
Yeah.
Yes.
This
And
is
so-
for a young subject
Uh-huh.
and for an elderly subject.
Do you have a guess about the physiological mechanisms that you're showing?
But maybe, since in the end the dynamics is regular in both cases, I can guess that it is due to the noise. Indeed, the level of noise are different in the two groups.
Right.
I mean, physiological noise. So for young people, maybe it's normal to have a noisy physiological system, let's say, cardiovascular system.
And for elderly, it stops.
It's less. Yeah, we can imagine that when there will not be no noise.
So, from what I understand about heart rate variability, like if you overwork your system with exercise, or if you're feeling sick, it tends to diminish heart rate variability.
Okay.
Is that related?
Allora, feeling sick or under stress, honestly, I don't know. But we did some analysis in pathological subjects. For example, subjects suffering from atrial fibrillation. And the dynamics, I mean, you can find, if you're interested, here you can find a more complete analysis. But in the end, we find that the dynamics is regular. So we can expect that some pathologies does not modify the dynamics, but the level of noise changes. But for this aspect, the expert is my colleague Andrea Scorciglia and co-authors. So you can refer to the other
Can you use this to
paper.
map your aging? So, you start to see your aging process, perhaps, like as you get older.
Yeah.
Yeah.
Yeah, there are several consequences, and it's really interesting to analyze them. So my last slide, why this? It's
Thank
for
you.
Thank you for the question.
Okay.